Hi all, this is Dr. K. Raghuram Mohan Reddy, Associate Professor, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. The course name is Unconventional Machining Process. The topic is Materials Addition Processes Part 3. It comes under Content Beyond the Syllabus. Okay, so here we are covering the additive manufacturing methods. Okay, so at the end of this session, student will be able to understand the rapid prototyping fundamentals and various techniques involved in rapid prototyping. Okay, right. Now, fused deposition modeling, FDM. Fused deposition modeling, in short, it is FDM, is the second most widely used RP technology after stereolithography. Okay, so after stereolithography, fused deposition modeling is the next widely used RP technology. Okay, the process is unlike all the other RP processes because a laser is not used to produce the cross-sectional layer. Okay, instead, the model material is applied directly in a semi-liquid form from a CNC controlled extruded head. Okay, right. FDM, fused deposition modeling, is the favored type of RP process when tough plastic components are needed. Okay, the process depends on building up the model layer by layer using thermoplastic 0.003 mm diameter filament. Okay, the filament is unwound from a coil and supplies to an extrusion nozzle as shown in this figure. Okay, so here the filament is passing between these two rollers. Okay, nothing but coils. Okay, right. Here's nozzle plus heating element. Next, jet motion for new layer. Okay, molten material and motion in XY plane for this one. Okay, right. The filament melts as it flows through the heated extrusion head and emerges as a thin ribbon through an exit nozzle. Okay, right. The FDM system operating software imports a CAD file. Okay, right. The software then orients the part of the optimum building, slices the model, and creates the path generated by the operating software, laying down a very thin layer of molten material. Okay, right. One layer upon another, the model is built from the bottom up. Okay, the required object is produced as a three-dimensional solid part in a single stage without need for tooling. Okay, each formed surface layer is machined with a similar cutter prior to the application of the next layer of the order to control the flow of polymer, and an evenly distributed layer is obtained. Okay, right. In the operators shown in figure 2, see fused deposition modeling schematic here. Okay, the nozzle is mounted on a mechanical stage which can be guided around by CNC code, and the viscous ribbon of polymer is gradually built up from a fixtureless base plate. Okay, so here you can see the setup here. Filament supply will be going like this, FDM head and object fabricated here, XYZ stage system here. Okay, so in the XYZ coordinates the table will have to move. Okay, right. As the nozzle is moved over the table in the required XYZ geometry, it deposits a thin bead of extruded plastic to form each layer. Okay, the plastic hardens immediately after being squirted from the nozzle and bonds to the layer below. Okay, right. The entire system is contained within a chamber which is held at a temperature just below the melting point of the plastic material. Okay, right. A second nozzle may extrude a second material if required. Okay, so we can maintain two nozzles. Okay, right. When the first layer is complete, the nozzle moves upward by one layer thickness and the process begins again. Okay, the part is easily removed from the platform, supports are dissolved, and the part becomes ready. Okay, many parameters are involved in building a part, such as the basic part design, the material selection, tool path, layer thickness, and part orientation. Okay, right. The time to build the part, cost, strength, and accuracy of the part depending on these parameters. Okay, several materials are available for the process, including what is this ABS? Okay, acrylonitrate, butadiene, styrene. Okay, and medical grade ABS E20. Okay, a thermoplastic polyester based elastomer and investment casting wax. Okay, so ABS offers good strength, and more recently polycarbonate and poly, that is phenol. Okay, sulfone materials have been introduced which extend the capabilities of the method further in terms of strength and temperature range. Okay, for simple parts there is no need for fixturing, and material can be built up layer by layer. For complex parts with inner cavities, unusual sculptured surfaces, and overhanging features, it is sometimes necessary to create support structure for any overhang sections of the model. Okay, support structures are later removed by breaking them away from the object. Right, a water soluble support material that can simply be washed away is always also available. Okay, right. Advantages of FDM. Okay, quite non-toxic and office-friendly process. Okay, fast for small thin shapes, produces strong parts, cost effective, no need for part cleanup, able to produce multicolored parts using colored ABS. Okay, disadvantages of FDM. FDM is fused deposition modeling. Okay, right. Slow when making large cross-sectional areas, has to use additional support material, relatively low accuracy and poor surface finish, unable to make complicated parts, limited number of materials available. Okay, right. Next one, multi-jet modeling. In multi-jet modeling, in short MJM, a printing head comprising 96 jets oriented in a linear array builds models in successive layers. Okay, so each jet applies a specifically developed thermopolymer material only where necessary. Okay, now look at this multi-jet modeling principles in this figure. Here, material supply. Okay, this is prototype, this is platform. Okay, so here jet move up and down directions, so this can be the top view. Okay, this is the top view of this one. Okay, so it can be moved in this direction too. Okay, so as shown in figure 3, the MJM means multi-jet modeling head shuttles back and forth like a line printer, that is x-axis. Okay, like this. Okay, building a single layer of what will soon be a three-dimensional model. If the part is wider than the MGM, that is multi-jet modeling model head, the platform repositions y-axis to continue building the next layer. Okay. This process is continued until the model is complete. Okay. The large number of jets allows fast and continuous material deposition for maximum efficiency using inexpensive thermopolymer. Okay. Now, ballistic particles manufacturing. In ballistic particles manufacturing, in short, it is BPM. A stream of molten material is ejected from a nozzle. Okay, see here, this is nozzle. Okay, next the material separates into droplets. Okay, these are the droplets. Okay, which hit the substrate and immediately cold weld to form a part. Okay, so it hits the substrate or base material and immediately cold weld to form a part. Okay, right. This is support material nozzle. This is part material nozzle. Okay, so usually we do not want the support material. Okay, so that it should be weak. Okay, whereas this one support material. Okay, whereas part to be make, that must be very strong. Okay, so this molten particles will have to be high strength. Okay, this right. The material stream may be a drop on demand system or continuous jet using piezoelectric transducer that excites the nozzle at 60 H. Okay, the nozzle excitation forces ensure the production of a stream of small regular droplets with uniform spacing and distance. Okay, so here the frequency is with 60 Hz. The piezoelectric transducer. Okay, right. Right. So what is this one? Ballistic particles manufacturing. So it is forming with what? Droplets. Okay, right. See here in PBM, okay, parameters include temperature and velocity of the droplets and the electronic charge they require when the this is ballistic particles manufacturing. Okay, BPM. Okay, when the stream is ejected, which is used to guide the droplets to the surface. The temperature controls the speed at which the molten metal droplets solidify. Furthermore, the deformation and placement accuracy of the droplets depends on its velocity. Okay. This process uses CAD generated three-dimensional solid model data to direct the stream of material, maybe waxes, plastics, photocurable polymers, ceramics or metals, at a target building three-dimensional objects in much the same manner than that an inkjet printer produces two-dimensional images. So here CAD means computer aided design generated three-dimensional model will have to be the input for this. Right. The object is built using a 3-axis robotic system controlling a piezoelectric inkjet mechanism for shooting particles of the material onto a target and producing multiple cross sections. Okay. A second material supports any overhanging structures on the path. Already we have discussed that. Let us say if we want this one, okay, here we have to give some support. So these secondary supports will have to be removed later. That's what here we have discussed. Okay, when it is overhanging, okay, so it will fall down. So here we have to make one support. That's what here stated. Okay, when the product is complete, it is placed in a bath that dissolves the support material. Okay, so after that, this will be dissolved. Okay, a limitation here is that the support material cannot be completely enclosed by the construction wax. Okay, right. Advantages of BPM. Okay, ballistic particles manufacturing. The ability to perform in microgravity and vacuum environments provides the production of parts in space and for advanced materials research. Okay. Second one, the method can, however, be extended to other materials that easily melt and solidify, such as thermoplastics and metals. Okay. Next, third one, important one. No post-production finishing is required. Okay, and tolerances of plus or minus 0.01 mm can be achieved. Okay, right. Wax models for investment casting can be produced without the need for dies. Okay, it allows the application of different materials or colors in a single part. Decreased turnaround time, increased productivity, and improved material properties make the BPM technology economically attractive. Okay, the method produces rapidly solidified microstructures in situ. Okay, near full density and net shape parts in a unit operation are possible. Okay, next last one, shape deposition manufacturing. Right. Shape deposition manufacturing is a new fabrication methodology for automatically building up material layers to form three-dimensional complex shape multi-material structures. Okay, the process combines the advantages of solid freeform fabrication, that is SFF. Already we have discussed in the previous presentation. Okay, so that is easy to plan and does not require special fixturing, arbitrary complex shapes and heterogeneous structures, with the advantages of conventional machining, that is high accuracy, good surface finish, and wide scale availability of existing 3 and 5 axis CNC milling machines. Okay, right. In addition to the rapid prototyping of complex shapes, selective additional material processing enables the fabrication of multi-material structures and permits prefabricated components, okay, prefabricated components to be embedded within the growing shapes. Okay, the goal of SDM is therefore to automatically manufacture parts that are strong, geometrically accurate, and have a good surface finish. So look at this figure, shape deposition manufacturing, SDM. Okay, right, shows the manufacturing steps which are as follows. Okay, this is the support material. This should be light strength, that's why it is in light color. And part material, this should be strong. Okay, so this is the deposit and this milling head. Okay, so it will here depositing, here removing. Okay, understood? Right. So here it will go like this and it will come like this. Right. Let us discuss the points here. As per this figure, look at this figure and just let us discuss. A CAD model Okay, out of this one, CAD model is the input, so we have to make a note on this. Computer aided design model is first decomposed into thin layer representations. That means in terms of slices. Okay, a layered segment is deposited as near net shapes. Okay, the thickness of that layer depends on the local part geometry and the deposition process constraints. Okay, third one, a layer of sacrificial support structure is simultaneously built up support and create a fixture for growing shape. Okay, so already we have discussed that when it is overhanging, we have to give some support. Okay, right. The layers are machined to a net shape before additional material is deposited. Okay, the sequence for depositing and machining the part and support material is repeated to form the entire shape. Okay, after the entire part is built up, the sacrificial support material is removed to reveal the final part. Okay, so these are the references associated to this. So with this, let us conclude. Thank you very much.
Like, share, and subscribe. Hit the bell icon for more updates.